Hey everyone, Mr. Newman here, and today we're going to learn about properties of real numbers. Basically, there are 6 overall categories of real numbers. The first one are natural numbers. You might call these counting numbers. They're 1, 2, 3, 4, 5, 6. Any positive number that doesn't have a decimal or a fraction in it is a counting number. And that we call those the natural numbers. Whole numbers are just the natural numbers along with 0. So 0, 1, 2, 3, 4, 5, 6, 7, that ... means going on forever. So 3,523, 8,643, any of those numbers, any of those positive numbers are whole numbers, and with the exception of 0, are also natural numbers. Integers are the positive and negative whole numbers. In other words, I put the ... there because even though I'm not writing it down, I mean to include -4, -5, -6. And so -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, on 8, 9, 10, and so on and so on. All those are integers. So if I use the word integer in class, I'm talking about either a positive or negative whole number. Rational numbers are any number that can be written as a fraction of integers. So 1/2 is a rational number because it's a fraction. 3 is also a rational number because you can write it as 3/1. Irrational numbers, by the way, ratio is another word for fraction. So that's how I remember that rational numbers are numbers that can be written as a ratio or as a fraction. Irrational numbers are any number that cannot be written as a fraction of integers. Notice the IR in front, that means the opposite, like irrational or irreligious or irrespective. So ir here means the opposite of rational numbers. Those are ones that cannot be written as a fraction. Real numbers are any number that you can put on a number line or can be placed on a number line, and that includes all the numbers above: natural numbers, whole numbers, integers, rational numbers, and irrational numbers. All those are our real numbers. Now, I want to draw your attention to the diagram over here because this shows us which numbers are always which other numbers. In other words, natural numbers are the smallest set, so that's the fewest numbers out of all of these numbers. The numbers 1, 2, and 3 fall into there. Whole numbers include all the natural numbers. So if something is a natural number, it also has to be a whole number. Remember that whole numbers also just include the number 0. Integers include all the whole numbers and all the natural numbers because they include the positive and the negative whole numbers, or the opposites of whole numbers. Rational numbers include all the integers, and then we get to our first non-inclusive set. So irrational numbers do not include rational numbers. In fact, those are separate. A number cannot be rational and irrational. But real numbers include all of the numbers, rational numbers and irrational numbers. Let's look at some examples to build intuition. Natural numbers, I already listed them, are 1, 2, and 3, but if I skip a few, there's also 8 and 42, 8,016, and 121. All of those are examples of natural numbers. Whole numbers are all those numbers, but also including 0. I could also write other numbers like 5, 6, 7, 8, but I'd be writing for a very long time if I kept writing and tried to write all the whole numbers. Integers are all those numbers, but also negatives. So 0 is an integer, 1 is an integer, -1, 5, -22, 38, -1,000,001. All those are integers because notice that they do not have any decimals or fractions. Rational numbers are numbers that can be written as a fraction. So 1/2 is an example of a rational number, but it doesn't have to be a proper rational number. You could have 25/3. That's also a rational number, or a mixed fraction. 1 is also a rational number because you can write it as a fraction. You can write it as 1/1. -5 is also a rational number. So any number that shows up above, any integer, like that diagram I showed you above on the paper, all those are rational numbers. -5 you can write as -5/1. 0.3 is also a rational number because even though it's a decimal, you can write that as a fraction. We call that 3/10. 0.3 is 3/10, and you can write it as the fraction 3/10. 0.6 with that line over it means 0.66666 going on forever, and numbers that repeat like this can also be written as a fraction. In this case, 0.6 repeating is 2/3, so that's also a rational number. An example of an irrational number would be the square root of 2. Another common one is pi. Now these numbers, if I tried to write them out as a decimal, I'd have to write out a bunch of numbers and put a ... at the end because I can't write them all out. Likewise with pi, that's 3.14159265. Some people say, okay, well, this number, you've heard the expression, this is a decimal that does not repeat and never ends. But when I first saw this, I said, hey, look, it does repeat. 1414. That's not what we mean when we say repeating. Look over here at 1/7. 1/7 is a repeating fraction because it's 0.142857, 142857, 142857. You see what I mean? The 142857 repeats over and over and over. That's what we mean when we say a repeating decimal. The way we write that is we put a line over all of it. So 0.142857 with a line over all of that means those 6 digits repeat over and over. There is no section or no part of square root of 2, no matter how far you go out, before the whole thing starts repeating. So root 2 and pi are both irrational numbers. Some other examples of irrational numbers include negative root 11, square root of 2/3, and the square root of 1.2. So just because a number has a decimal or fraction in it, if there's a square root, that makes it irrational. That means you cannot write it as a fraction. Now, real numbers include all the rational and irrational numbers. So all the numbers, in fact, the natural numbers, the whole numbers, integers, all of them that are written here are all examples of real numbers. So I'm not going to write them down again because we'd just be writing down all the same stuff that we've already written down. So one of the things you're going to have to do is you're going to have to look at a number and decide whether it's rational or irrational. So let me give you some pointers for that. Rational numbers, if you see an integer, that means without a decimal or fraction, it's going to be a rational number because you can always put it over 1. Fractions, of course, are always rational numbers because that's the definition of a rational number. That is, fractions without a square root. Terminating, that means ending decimals, can always be written as a fraction. 0.1528, because it ended, I can write that as a fraction. Right now, I don't care that you know which fraction it is, you just need to know that you can write it as a fraction. Repeating decimals, likewise, if the entire thing has a line over it, or if there's any line that repeats over and over, that can be written as a fraction. So it's a rational number. A rational number. Irrational numbers, however, are decimals that are non-ending and non-repeating. That's often signified by a ... at the end, and you don't see any obvious parts that are repeating. Likewise, pi is always irrational. That's a favorite one that people test and people like to point out and use. Square roots of non-perfect squares are also irrational numbers. So the square root of 2, the square root of 3, the square root of 5, the square root of 8, all of those are irrational numbers. In fact, I'm going to include any roots that are not perfect. That includes cube roots or fourth roots or larger ones. Now let me go ahead and list the perfect squares because that's helpful when deciding what whether a number is an irrational number or not. Perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225, which is 15 squared. And yes, you should have all those memorized. If you do not yet, I would suggest making flashcards of what exactly they are, so you can, off the top of your head, know that 9 squared is 81, or 121 is 11 squared. All right. Now for a little bonus. This is the proof that the square root of 2 is irrational. A lot of people go, well, maybe we just haven't found it yet. But we even have a proof that it cannot be it. Now we're going to use proof by contradiction in this part. This means that we're going to assume something is true, and we're going to show that it's impossible. Okay? So the thing we're going to assume is we're going to say, well, what if we could write the square root of 2 as a fraction? And not just that, but of course you can reduce any fraction. So we're going to reduce this fraction right here, and we're going to say that fraction, when you reduce it, is p over q. Maybe we just haven't found it yet. Maybe it's some really, really long number that computers can't even figure out yet. So square root of 2 is p over q, and that's a reduced fraction. Reduced, by the way, means, like, for example, 3 over 6. If I want to reduce 3 over 6, I divide the top and bottom by 3, and I get 1/2. So 1/2 is the reduced fraction. Now, first thing I'm going to do is I'm going to square both sides, which is perfectly allowed. I get 2 and p squared over q squared. Next, I'm going to multiply both sides by q squared. That puts q squared on the left and 2q squared on the left, and then p squared on the right. Now, something interesting happens here. Remember, we reduced this fraction, and one thing I forgot to mention was that p and q are integers, okay? That's one of the things to be rational. It's assuming that they're rational, and we're assuming that thing we're pretty sure it's wrong, but we're going to use proof by contradiction. We're assuming that p and q are both integers here. So that means that q squared is an integer. But if you multiply any integer by 2, you get an even number. That means p squared has to be an even number. So p squared's even. Okay, so what? Well, if you think about any number, if the square of that number is even, then the original number has to be even because you're multiplying by 2 to get the number. So that means p must also be even. If you don't believe me, try it out. Try to find some perfect square that's even, where when you take the square root, it's not even anymore. You can't find one. So if p squared's even, p must be even. But wait a second, this gets a little trickier. If p is even, p squared is p times p. That's an even number times an even number, which means that's divisible by 4. If p squared is divisible by 4, we can divide both sides by 2, and that means q squared must be divisible by 2. So q squared is even. Okay, so q squared must be even. Well, the same thing applies. If q squared is even, then q must be even as well. Because remember, I said you can't find any perfect square that's even where the square root is not even. So q must be even. And we've arrived at our contradiction because if you look up here, we assume that p over q is simplified, but we just showed that p must be even and q must be even. But an even number divided by an even number is not reduced because you can divide the top and bottom numbers by 2. So what happened? Well, we just showed that that was impossible. In other words, the square root of 2 equals p over q is wrong. There's no p and q integers that are not reduced that can make this. And of course, you can reduce any numbers by dividing out the factors. So that means something more bigger must be here. This square root of 2 is irrational and is impossible for the square root of 2 to write as a ratio of integers. Thanks for watching, and I hope you learned something.